So we're looking at few phenomena that we get to observe in our day-to-day life, and that is related to self-induction. So one of that is sparking. So when we have the switch, right? So switch in a house and all of that. It looks like a 8 though, but yeah, I think looks decent now. That's supposed to be a switch. So when we switch on and switch off, sometimes you get to see this. You get to see some sparking. So when the tap key is released, the sudden interruption of the current can cause spark at the contact. So even with your physical, lab and all of that, you have this big kind of switches. I'm not doing a good job over there. Have you guys seen this? It's a switch basically. So your physics labs might have it. So when you're releasing and all of that, when you're putting in releasing and all of that, if it has a pretty decent voltage, you get to see this. This is due to the high voltage generated by self-induced EMF, which can ionize the air around, and thus we get to see a spark. This is a smart usage. I like it. I liked it when I read it for the first time. To minimize the effect of self-inductance, non-inductive winding technique can be used. So you don't have to spend extra money, you just have to be smart. How is that? This involves winding the coil in such a way that the magnetic field produced by adjacent turns cancel each other out and reducing the overall inductance. It makes sense, right? So it's just about being smart at that moment of time. So one more usage or point wherein we get to see this is electromagnetic damping. Damping has to do with slowing down stuff, right? The self-induced EMF can also cause electromagnetic damping. This is a phenomenon where the induced current opposes the change in magnetic flux, thereby damping the oscillation and stabilizing the system. So this is a possibility. Okay, guys, I think, yeah, I have this many. You can have a look.